Okay, good. All right, so today's, so last time we did last time it was Solovey's theorem, right? So the theorem was Solovey to dr. Then there is sorry. Then there is a supercompactness measure. Omega 1 R. I think some people don't like this notation. I don't really know why, but I'm used to it. It will be hard for me to change to anything else. This is the countable subsets of reals, right? So let me remind you what supercompactness measure is. Those X is a non-countable set. And the subset of our set of omega on X. Right? So remember P omega on X, this is the set of sigma subset of X. Sigma is countable. So we say mu is a supercompactness measure if A or mu is an outer filter, mu is a countable complete outer filter. The omega 1 of X. E. So mu is fine. Mu is fine. What that meant is that for any A in X, the set of sigma in the omega 1 of X such that A belongs to sigma, this has measure 1. And E, mu is normal, right? Mu is normal, and this is the one that's a little bit different. So for any F which maps P omega 1 of X, where F is a function from P omega 1 of X into P omega 1 of X, such that for measure 1 many sigma in P omega 1 of X, right? F sigma is a subset of sigma. So pointwise image of F ends up being a subset of sigma. That is measure 1, right? Then there is some A in X such that the set of sigma in P omega 1 of X with the property that A belongs to F of sigma I should put F of sigma here. It should be F of sigma. A belongs to F of sigma. This is measure 1, right? So this is going to be used in, like, the most trivial place that you should think of is Walsh's theorem. F of sigma will be set of things from which you can define the witness, right? So you want to prove Cauchy's theorem, so you have some sigma 1 formula, and some members of sigma define, you look at all the possible things in sigma that you can use to define a witness, and then you need to pick one in order to prove Cauchy's theorem. And this is telling you to do it. Okay, so we care about this notion in, if you assume ZFC, then you can change this to the ordinary version, right? Like we do it, but we won't without ZFC. All right, so we want to prove today Woodman's theorem. Which basically says, assume AD, I think we probably need DC as well, or just AD plus, assume AD plus DC, then so assume that, and then pick, suppose X is any set, let me call it S, yeah, because X is a variable, is any set such that there is a surjection on rails onto S. Okay, surjection. I mean, yeah, surjection, not by surjection. Then there is at most one super compactness measure let me see if I'm saying this right. I think I want to say ADR. So he proved something more. I mean, there will be a lemma which it will tell you. So the way he proved it is that you identify. Basically, you look at the Solovey's proof, right? So Solovey, what was Solovey's proof? You look at sigmas which are closed under, basically are closed under certain strategies, right? Strategies for player 1 or player 2, or whichever one is the good one. So you look at countable sigmas that are closed under such strategies. I mean, pick a strategy and then look at sigmas which are closed under them, right? So pick like these clubs, and then look at the filter generated from it. So Solvay actually showed that that's an ultra filter. Okay, so now what wouldn't show is that if you just assume ZF plus DC, then any ultra filter you pick, any super compactness measure you pick, will contain all of these sort of clubs. S should be S, yeah. But then under ADR, we know that there is such a super compactness measure, so then therefore it should be the unique one, right? So imagine you had another super compactness measure. We already know that under ADR, the club filter, the one that's generated by clubs, in the sense that you look at all sigmas which are closed under some function. Okay, that actually generates a club. I mean, an ultra filter, and I wouldn't prove that if you take any super compactness measure, those clubs will have measure 1, and so it has to be. So there can be only one. So there is exactly. So now why don't we change this? There is exactly one. There is exactly one super compactness measure on.
Viggo, did you say you will need ADR also in the proof that there's at most one?
Well, I don't know if you get there is at most one. because I don't think the proof shows that there's at most one. Because you could, I mean, the Wooden's proof shows that whatever supercompactness measure you have, it has to contain the club filter. I mean, I'm loosely speaking here, right? It's not, these are not exactly what you work on. But anyway, he identifies a collection of sets that any supercompactness measure has to contain. But then Solovay's theorem says exactly those sets that generate a measure. And so therefore it's only one, right? So just from AD, there could be two measures. Okay,
I see.
I didn't think of it.
Yeah, okay, thanks.
Mm-hmm. But right. Anyway, so let's go on. So let's pick an S. So I'm going to work towards the proof. Yeah, fix an S. So now fix. Yeah. Am I frozen? Oh,
All good, all good.
fix S as in the theorem, and pick a subset of the omega 1 of S, and also phi, which maps the reals as phi surjection. Okay. Right, so now we look at the game associated to A. So so he calls it, I think this is the following game. So it's the game that Solovay played. So we have x0, x1, except now we're just doing only singles. And one wins if and only if. Okay, the rules are that xi has to come from S. And one wins if and only if the set they produced belongs to A. Okay, so now we want to say, so this is a game on members of S, right? S is just any set. And so we want to now say what it means to be a strategy for this game, but on sets of on reals, right? So what does it mean to say? So what is a strategy for this? What is a strategy for this game? I mean, okay, so it's just kind of, it's obvious what the strategy is, but what I mean is, how could you translate that onto reals? Because we have this coding here. Yes, so you want to say, okay, here's the definition. We say tau, which is going to be a function, which is basically a function, a subset of what is, so it's going to be some kind of function, is a quasi-strategy. For one, if, okay, so one, so if you take a position in that game, such that one has to respond, two has to respond, and two responds. That means P belongs, P is what? P is so P is mapping what, 2 to the n plus 1, right? Two responds, that means into reals, then and P is in tau, right? So this means it's a run of the game where 2 is about to respond. Then you have to say, no matter how 2 plays, you're still in the domain. And for any x in R, how P followed by x belongs to tau. So it doesn't matter what 2 played, you stay in the within the strategy. And 2, if it's one's turn to play, which means you now have this type of function and in tau, then now, so here it's for all, then here we have to say there is an x such that P followed by x is in tau. Now it's not unique, right? You cannot say it's unique because x is not. I mean, you could, if R was well ordered, you could then pick a particular one, but now we cannot. Okay, so this is what the strategy is, and why is this any good? Well, we could now ask, map this real sum by pi, right? We have this. We had the surjection from reals onto S. So you have some strategy on reals, but now you can look at the values that pi gives you. Then you ask if that belongs to A, right? And now okay, so that motivates the next definition. I guess the remark here is, what happened? Yeah. Oh, I see. I was writing on the last page. Oh, how did this happen? Okay, now I cannot move it. Oh, maybe I can. Yeah, I can do like this. Okay. So the remark here is that, let me just write it here. Now, we can think of sort of pi composed with tau as a strategy for one in basically, right? Okay. Now we say, all right, so here's another definition. Suppose tau is a fuzzy strategy for pi is a map. Subjection, right? Okay, so we let, but this is the sort of the club, should really be called C. Why don't we call it C? C pi. Now this will be the set of all sigma in P omega 1 of S, right? So basically you want to say sigma is pi now closed. So what that means is that basically you want to say sigma we can enumerate sigma in a way that it becomes that it becomes a run of the game in which player 1 plays according to tau. So we say there is a So there is an enumeration. So there is F or replay. So there is P from omega onto reals. Right. So this is going to be mimicking the run of the game associated to some set onto reals, right? Such that for every n in omega, P distributed to n is in tau. So you're staying within tau, and your sigma is the range. Is the range of I. So you cannot say P, right? So it's the range of basically pi composed with P. Yeah. So sigma, you can write sigma as an output, as the sort of the thing that the 1 and 2 are trying to build, right? Okay. I'm not sure if the name is yeah, I guess you can say it's part of, yeah, because when can you write sigma as when sigma belongs to this set? If I had the, so sigma is countable, right? If I had the property that any sequence I take, which is according to tau, there is an x, so the even thing, there is an x that I can in sigma such that I added it, it's still according to tau, then I can write, then I can really find such a sequence, right? So remark, sigma belongs to C by tau if and only if for every P in, for every, oh, let's see, for every n in omega and for every P which enumerates fixed n reals, for any n for every, so I guess I want to say, what was it, even? Yes. So any even, so I could say here, right? Right. So when I take pi and I compose with p, so the range of this belongs to sigma and is in, yeah. So if you have that property, this property implies that there is some x in sigma such that, so I guess you want to say there is a real, really, right? There is a real with the property that pi x belongs to sigma and e followed by x is in tau. So if you have this prop, right? I mean, from one direction, it's obvious. If sigma, if you can write your sigma, if there is an omega enumeration, then you have this property, right? Because your enumeration guarantees that you are always in tau. But here, what's on the right side, it's just saying that only at the even steps you have to care about this. Okay, but the even step, the odd step, it doesn't matter what you do, you're always inside tau, right? So at the even step, you can just pick one, it's good. Okay, so, right. So here is another definition. So we say A, which is a subset of P omega 1 S is determined. if and only if there is a fuzzy strategy pi as pi tau sorry, if and only if there is pi, if and only if there is pi projection, and I guess we could fix pi, things will still be okay. And tau, the quasi strategy, relative to pi, such that C, I should call this, I call this guy C. So C pi tau is a subset of A, or C pi tau is a subset of T omega 1 S minus A. So A is determined if all the plays according to tau belong to A or they belong to the complement. And I mean, okay, you can think a little bit. It doesn't really depend what the coding is, right? If you had another coding and another strategy, these sets intersect. In fact, a stronger thing is true. Let mu be things of the form pi is a surjection, and tau is a quasi strategy. It depends on pi, right? Relative to pi is a filter, is a fine filter, right? Is everything okay? You guys not making a single sound?
Everything fine. Everything okay.
All right. Okay, so I mean, you could. It does not depend on pi, because if you had two codings, the reals can be coded by two. Two pairs of reals can be coded by one. So you could prove, that this concept does not depend on pi and tau, right? If it's not like one pi tau will get into A and then another pi tau will get into the complement. Okay, so this I would leave as a homework. Yeah, so we decided to do this homework. And here's the main theorem, main theorem from which you can deduce the other theorem, Wooden's theorem. This is also Wooden, right? And this just needs ZF plus this. So suppose S is any set such that, but this is important, such that there exists surjection and okay, so if okay, so suppose S is any such that this, and suppose mu is a super compactness measure on the omega 1 of S. Okay, so then oh, I should have also suppose one more thing. Suppose tau is a quasi strategy for one relative to I, right? Then the set we define, this club, let's measure that. Okay. And so the filter that we generate with these sets, no matter what supercompactness measure you take, they always have measure one. Okay, so proof. All right, so suppose mu 0, so B equals P omega 1 of S minus C pi tau as measure 1. Mu P is all right, so we're now going to play a game, right? So fix sigma and B. What's going to be the idea? So we want to produce a member of sigma, right? That belongs to C pi tau, right? We want to produce some sigma in B, which is closed on the tau, basically. Okay, but that involves picking moves for 2, right? Okay, but we have this measure mu. Okay, so we want to make. I mean, if you just do it randomly, we have to keep picking. Okay, so but then you say, okay, measure 1 many sigmas. Tau is giving us the same value on measure 1 many sigmas. So at that stage, it's just like proof of pi 1 determinacy. When you say, okay, measure 1 many things would give me exactly the same value, then that's the value you play. So it's we want to prove that there is a sigma in B that can be enumerated as a run of the game according to tau. So it should be so it will be closed under tau, but it's in the complement, right? Okay. So we look at the following game. So consider this sigma. This is a game, and the game is what? Basically, one is two claims. My sigma, yours, that sigma is my strategy is closed under it. Yeah, the tau is closed under it. I mean, your sigma is closed under tau. Okay, so one is playing, one is challenging, right? How does one challenge? Well, one keeps playing something, and then 2 has to cover it. 2 has to cover the move of 1, and then at the end 2 has to make sure that it gets into sigma. So one is playing members of S, and etc. And 2 is responding with reals, with sequences of reals. Right. Okay, so what are the rules? Xi belongs to sigma. Remember, sigma is in sigma is in P omega 1 of S, and so maybe I should call this guy something else. Let's call them okay. And okay, so now y's have to be according to tau. Yi is in tau for every I, and yi's are increasing, right? So 2 is producing a run of the game. This means yi plus 1 extends yi. Remember, tau is a finite sequences of reals, right? And so this notation says that yi is longer than yi plus 1 is longer than yi. It's continuation. And then, of course, the other rule is that xi has to belong. So this is again for every I, and xi has to belong to the set of I of the reals that 2 has produced. R is a real in, so R belongs in the range of, R is in the range of yi, right? Okay, so what's happening in this game? 1 is challenging 2, right, to produce a covering of the members of S that she's playing, so that the end result, and 2 is trying to show that whatever you play, I can still enumerate my sigma according to the strategy. Okay, so that's it. And what? I mean, okay, 2 wins if she can keep doing it, right? So 2 wins if and only if 2 can always play. The game lasts omega steps. Lasts omega steps. Okay, so it's closed for 2, open for 1, right? It's closed for 2 because what? 2, it's only just depends on the in each step for 2, whether she lost or not just depends on the play up to that point. Nothing else. So it's closed for 2, and it's open for 1 because you can, because it's closed for 2. Okay, so that's the remark. The sigma is closed for 1. Right? Is everything okay?
Yes, yes.
Am I correctly understanding this? The first condition is for player 1, the other 3 are for player 2?
Yes.
Okay.
Yeah, you can think of them as rules. The winning condition is if 2 can always play. Meaning
Okay.
2 never violates any of the rules, right?
Like the last one, but the last one also is a rule for player 2 because player 1 first plays it on and player 2 then plays I1. Okay.
Right.
Okay.
So this wait a minute, I forgot the key point. This has to be subsets. So 2 has to stay within sigma, otherwise it makes no sense. Otherwise 2 can of course win this game, right?
But
The challenge for 2 is to enumerate sigma as a play according to its strategy. And 1 is challenging. 1 is saying, no, you don't know that it's not close to according to your strategy, and just keeps playing these X's so that 2 cannot cover them. So this condition is key, that you have to stay inside sigma. But that's closed. I mean, at each step, whether 2 has violated the last rule or not just depends on the reals that 2 has produced. It doesn't matter what comes after that. The stage N 2 lost if she violated this particular rule. That's it. Okay, so this is a closed game. Now there is we don't have a strategy. It doesn't mean we have a strategy because it's the space on which we are playing this game is not well ordered. So that means we have multi-value strategy, right? So there's like, okay, so the game, it's a closed game. One of the players wins, but not by an actual strategy, but more like a multi-value strategy. So one of the players has a does one of the players has a winning multi-strategy. So that means at each stage you have many possible things you can play.
Sure.
Yes.
What's the difference between multi-strategy and quasi-strategy?
Well, I would in his paper he's calling the other things quasi-strategy. I would call nowadays people call these things quasi-strategy. So I don't know.
But
Yes.
like, you mean the same? It is the same.
Yes, but I don't want to use quasi-strategy because in this proof it had a very
But
specific.
okay.
Yes. Right.
But you did use it, right?
Yes. Yeah.
But you've used okay. So what's the difference between quasi-strategy as you've used it?
Well, the
As opposed-
quasi-strategy there was for some particular notion.
But this was, as far as I understand, like the notion that I can always stay within the strategy, and but I'm not unique,
Yes,
right?
but we used the word quasi-strategy for this very particular object, so I cannot.
Okay.
Like we already called something an apple, therefore we can never use apple to call other things. Yeah. So I mean, this just means that at each step you have all possible values, not just one. All right, but this means what? We have DC, right? See, we have DC. This is very important. That means if 2 wins this game, then she can enumerate sigma. So if 2 wins, then sigma belongs to this thing. Because 2 can keep picking moves. Now, what do? We take how we enumerate. Let 1 is going to just play all the moves, right? All of the values of sigma, members of sigma, and 2 is just going to enumerate them, right? Okay, so this is easy. Now, therefore, 1 wins. So 1 wins G sigma. Okay. Now, because 1 wins, we have actually one particular strategy, right? So it's a closed game, and closed games, remember, you win by playing non-losing moves. So let rho sigma be the winning, be the egg, be the non-equal winning strategy, winning multi-strategy. Okay, and now what we're going to do is we're going to attempt to create a run of the game in which so 1 is going to try to play according to these rho sigmas, 2 is going to respond, but then we want to use our measure to show that we can actually that measure 1 many things will give us the same answer. So this is this This is where we are going now. Okay, so let's look at the position in one of these G sigma games, right? All right. So now we forget sigma and we consider positions of positions in the G sigma game, but the generic game, not a particular anymore. So now suppose, right? Oh, I mean, I guess the thing to keep in mind is remark. Rho sigma is defined for all sigma in B. So for measure one many, for almost mu almost all many. So for mu almost all sigma, rho sigma is defined. Important. Okay. All right, so now let's pick a position. Let Q be alpha 0, S 0, alpha 1, S1. I should not call these guys S's. XI. Such that is such that for mu almost all sigma, Q is in P sigma, rho sigma, right? Q is according to rho sigma. Okay, so let's just take a position which is generic, so it's in all according to almost all strategies. And now let's see if we can identify a move that is according to almost all strategies, right? So we want to identify a move which is according to almost all sigma, all rho sigma. Okay, so because it's for almost all, so what do we have, right? So we have, right? So I mean, my assumption is that it's for mu almost all sigma, Q is in rho sigma. That means for mu almost all sigma, I have a response, right? So so we have what, let's call it star, instead of sigma such that there exists X in sigma such that Q followed by X is in rho sigma is measure one, right? Because for almost all sigma, rho sigma, right? We had for almost all sigma, rho sigma is defined. For almost Q belongs to almost all rho sigmas. Therefore, for almost all rho sigmas, we have a response. Okay, so now what we do, we use normality, right? So now let's call this set C. I already had something was C. Let's call this D. So let for sigma in D, f of sigma being the set of all X in sigma such that Q followed by X is in rho sigma, and pick, and by normality, right? So by normality, mu, we have some particular xi plus 1 in sigma such that the set of sigma with the property that Q followed by xi plus 1 is in rho sigma belongs to, right? Normality would give me 1 point that belongs to all of them. Okay, so what does this mean? What this means is that we can play infinite and produce an infinite sequence. So we can now get Q, which is an infinite sequence now. I mean, you have to think a little bit, right? Why? Because tau is also a strategy. Okay, so we can get an infinite sequence such that what? A for every I, Qi for every what I, even I guess, right? To restricted to I. Well, I guess it doesn't matter. Qi is in rho sigma, right? Because if you think of rho as a, yeah. And the y's are according to tau. So yi are according are in tau. Yi is y less than yi plus 1, and C xi is a subset of xi is in I R is in the range of yi. So why is this? Well, tau itself is a strategy, right? So what do? We say, okay, you play. I mean, you start out you play the one, so it's stage 0. Player 1 plays the point such that it belongs to measure 1 many. It's the first move according to measure 1 many rho sigmas, right? Okay, then tau is a strategy, so player 2 is extending it because tau is a strategy, so there is some extension for it. Remember what? Let's just go up to tau. Where is tau? So tau is a strategy, which means every time you give me, let's say x0, then I'm supposed to be able to find my y, right? So that's what 2 does. And remember, this is not a condition. So we don't have any fixed sigma. We're just producing an infinite sequence, right? Okay. And there is D. Okay, so 1, 2, and the D is that, maybe I'm not saying this right. Yes, I'm not really saying this right. What I want to say is that, so we can get Q and sigma. And sigma in B, such that this is subset. So okay, what is the sigma? We have at each step we have measure 1 many sets, right? So you produce, look at your x0, the tau gives you response, right? Now we have let's see. So what is it? You play x0. But it's fine. Sorry. Yeah. Yes. So just look where sigma is going to come. How we get sigma? So we know let d0 be let a0 be in mu and x0 in S be such that every sigma in A0, x0 is the first move by sigma. Right, so we already proved that player one, the measure one many things will play the same thing at the beginning. Now, tau is a strategy, right? So tau tells you, okay, so tau, there is some y, there is some x1, or I don't know, let's call, some y0 in tau such that y0 equals a0 a1 and x0 is pi of a0, right? So remember, tau is strategy on reals, so tau is going to produce reals, but you play your x0, pi is a surjection, so there is going to be some a0 such that a0 applied to pi of a0 equals x0. Okay, so that's by DC you can pick one. Okay, so you pick one and then you find an a1 which puts you inside tau. But you're now inside, but it's fine, right? So now we have so but remember rho sigmas are, so for all sigma in A0, x0, y0 belongs to rho sigma because rho sigma is a strategy. Sorry, not for rho sigma like this, but you have to be careful here. This is the step where you have to be careful. So now for all, what is my A1? Or yeah, let A1 now be the set of all these guys, right? Because why is this? Why can't I just set? Why what I wrote is bad? That for that, right? Why is x0 y0? Why is it may not be in rho sigma for almost rho sigma? Because of this condition. One may or two may already lose because of this condition. We're supposed to be inside sigma. So if two already lost, then you cannot do it. So what we need to do is pick a set that contains A1, but that's where fineness comes in, right? So we say let A1 now be the set of all sigma in P omega 1 S such that this little A1 that we played belongs to sigma. So this is measure 1. Let's call this A1 star. This is in mu, and A1 is A0 intersection A1 star. And now we have that. So this is in mu. And now I have, so for almost all, so for every sigma in A1, the pair we played, x0, y0, is in raw sigma. Right? Okay, but at each step, so I'm producing infinitely many steps, right? At step I, continuing this way, we produce AI I in omega such that, okay, what are the properties? The property will be one for every I, AI belongs to mu, two for every I, we produce that, and we also produce, so we also produce the sequence, right? We also produce x0, x1, let's see, am I doing this right? Yeah, I think I want to say that x such that instead of sigma, such that for every sigma in AI, this is x0, y0, x1, y1 up to xi, yi belongs to rho sigma. Yeah, this is what you want to say, right? And now pick a sigma, but then if I take a sigma, so now let sigma be in the intersection of AI, then we get a contradiction, right? Then we have that sigma now belongs to C I tau, as witnessed by exactly by these y's, as P equals, just take the union of yi. Yeah. Saying that it's in rho sigma means I mean that two hasn't lost. So that means this condition 2 is C is satisfied. Right, so this means condition C above is satisfied. Okay. So that's the proof. Is it okay, or please somebody say yes?
So at the end of the day, it's really just like in the proof of power indeterminacy, right? So
Yes. Yes.
at each stage, I just guess what I would probably respond. Like, no, what the other guy would probably play, and then I just take whatever I would respond to the probable play of the opponent.
Except we need to use fineness in this step. This is this
Can
step.
you comment how you use fineness here? Because I think I don't.
we know the measure is fine. So I know that the set of A1, I know that there is some Y0, right? But it doesn't matter which Y0 you pick, because the set of look at the coordinate A1, right? That set will be measure 1 anyway. So if I pick Y0, but then it was getting me out of almost all sigmas, then you are running into trouble. But no matter what Y0 I pick, which puts me inside tau, I am still on measure 1 many sigmas. Yeah, this is a key point here. Does it make sense? Imagine we're trying to produce this one. Right? Imagine you play the A0, which is on measure 1 many places. And now I have to do something for S2. So I say, okay, my tau is a strategy, so pick some extension of A0, which ends up in tau. Okay, but how do you know that now you are according to measure 1 many strategies? Because it could just be for every strategy, it could be that 2 lost already. And the losing condition is exactly this, because 2 has to guarantee that you are in sigma.
So in a way, fineness allows me not to only just take my typical response, but also according to a typical strategy.
Yeah, exactly. Yeah, exactly.
Okay.
And this A0 was played by almost all strategies, so it belongs to almost all sigmas for which that property is true. And then A1 is also coming from the move of 2 is also coming from almost all according to almost all. I mean, it's like too many strategies here. According to almost all the row sigma strategies, right? Okay, but this also gives you the uniqueness now, because this theorem implies maybe we right. Because why? Because under ADR, as shown by Soloway, right? That's what we proved last time. The set C pi tau as before generates an ultravolta. A super compactness measure. And so there is only one measure. So how does this kind of stuff? How do we usually use this kind of stuff? Well, I mean, why is this theorem useful? Because remember, we are doing something completely different, right? We want to get dense ideals on omega 1. Okay, the way we will use this theorem is that there will be super compactness measure on 2 sets X and Y, and X contains Y. Then we have the canonical super compactness measure on Y and the canonical measure on X, but then we can conclude that the projection of the canonical one on X onto Y is actually the canonical one on Y. Yeah, so that's the use. Okay, so then we have like a few minutes. And we started like 5 minutes late. So why don't I do at least one application of super compactness, right? So let's try to prove Walsh's theorem. Right.
Sorry, can I go back once, a bit to this uniqueness? Just can you just briefly repeat the last sentence?
So we proved what did we prove last time? That the Soloway what was Soloway's theorem? It was exactly these sets generate I mean, okay, you have to think a little bit, right? So we have some set S onto which reals subject. We know that there is a supercompactness measure on reals. So you can transfer the supercompactness measure from reals onto that set. But what is the how you do that transfer? Well, it's exactly via these clubs, right? Tau is now a strategy. What is Tau really? It's a strategy in solo base game on reals. Now you just apply surjection that translates onto sort of the corresponding solo base game on the set S. So this set generates an ultrafilter on S, just because it was generating an ultrafilter, just without pi. If you just look at closure points of tau, it's generating the supercompactness measure on reals. And so when you apply pi, it's generating supercompactness measure on S. Okay.
Okay.
Right. Okay, so here is the place we need. This one place we need. We will need a few times. So suppose we have. Suppose mu is a supercompactness measure on the omega 1 with x over S. Let's put it as. And oh, so I have to be careful. And f is some function from the omega 1 of S into V such that f is ordinal definable, basically. Let's say f is ordinal definable. And we also want not just that f is ordinal definable, but also f of sigma is ordinal. So we want maybe we want just f of sigma such that sigma such that f of sigma is OD is OD from sigma and members of sigma. From I mean parameters come from sigma and sigma itself, right? From is measure 1, right? Then Walsh's theorem is true for the product right. So what is this product? Well, this product is okay. I'm doing this a little bit too fast. I probably should take. Do I want to say that? Well, I mean, think of F sigma as some kind of structure. Yeah. So there's some language, there's some logic, first order logic, and things like that. So I mean, we're using first order logic here. So think of so this is what this is going to be. The equivalence classes. Okay, so we take. So what is this, right? So given we define equality mu on product of F sigma by So the product of f sigma, that just means functions from sigma to there, right? Maybe I should say what that is. Okay, let me just. Take product. Sigma is just a set of functions from the omega 1 of S into V, such that a set of sigma where f of sigma belongs to f of sigma. Let's measure 1. Right. Or you actually don't need that. You can say for every sigma. Yeah. You can say for every sigma, f of sigma belongs to that. Okay. And so for f in the product, you say f is equal to g if you only have a set of sigma such that f sigma equals to g sigma is measure 1. And okay, so we can interpret other logical symbols this way, right? So f sigma mu, the universe of this structure, is really just the equivalence classes. Is the set of f mu. F belongs to f sigma, and this is just a set of all g in the product, such that g is equal to f. Okay. Okay, then Walsh's theorem. Now it's what is Walsh's theorem saying? Right. So this is saying sigma mu satisfies some formula phi for f1. Sorry. f1. I'm going to drop mu. f2 go fn. If and only if the set of sigma such that f of sigma satisfies it. But we don't have choice. That's the whole point, right? These are not well-ordered structures. F1 P F1 sigma up to sigma blah blah blah. Fn sigma belongs to mu. Okay, so how would you prove it? Well, it's enough to do the existential case, right? So let me tell you the idea. Enough to do. So proof is by induction. So can assume is basically there exists u psi, right? So ignore f's, or we don't have to ignore f's. Okay, let's say, and right. Okay, so we can say, suppose one direction is always true. Right, I mean, right to left direction is, if you knew that this is measure 1, you'll get the other one. Is how you, sorry, if you know this was so high, assuming right, left to right is always easy. So let's do right to left. So suppose the set of sigma such that f sigma satisfies that exists u. Because now we need to find this function. That exists u phi u f1 sigma blah 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 fn sigma belongs to mu. Right, so where is my function that finds the u? Okay, so this is f of sigma satisfies u, so that u is ordinal definable from something, right? So for each, let's call this a. Now for each sigma in a, let b sigma be the set of things, set of a in sigma, such that there is a u ordinal definable from a and sigma. So there exists, let's say, b. Let me just write this here. Right. G sigma be the set of a in sigma such that there exists a b in f sigma such that p is ordinal definable in v, yeah, not in such ordinal definable from a and sigma, and f of sigma satisfies a psi b and fi vector sigma, right? So we know that mu almost all sigma g sigma is a subset of sigma, right? Because we assume that f, oh, I should have said f of sigma is just, sorry, it's not just that it's ordinal definable, it's subset of hot sigma. Its members are also definable. Where did I say it's ordinal definable? Where is that? So why don't I more clarify this a little bit more?
And you can also say it's true for every sigma, right? I mean, it doesn't change.
Yeah, such that this is, yes, you could say it's. You need some kind of f of sigma is somehow definable, so that you could reduce the parameters onto sigma. That's sort of the key. The key idea is that I know my witness exists in f sigma, but I can find parameters in sigma that give me these witnesses. So second order objects kind of flip down to first order in some sense, right? So okay, so now we have, for measure one, many sigma g sigma ended up in sigma, right? So why do I need that condition? This condition that f of sigma is actually in hot. So all of its members are ordinal definable, exactly because that's what I'm using here. I know that there is a witness, and I know that that witness is ordinal definable from something inside sigma. So I just take all of the things from which you can define such a witness, and now using normality we fix one.
I don't think what you wrote is what you mean, because you define G sigma as all the A's in sigma, such that something holds, and now you just said G sigma is a subset of sigma, which is true by definition, right?
And non-empty, I mean.
Okay.
So pick some A in the set S, in the best set A, such that for all mu almost all sigma A belongs to G sigma. So A is my parameter now, but B is ordinal definable from A and sigma. So now I can define a canonical witness, pick the least ordinal definable one, right? So now let F sigma be B, where B sigma is the least of the A. Just a second. Hello? Okay, I will finish, so I'm finishing. Okay. Sorry, all of this is recorded. Our seminars are extremely like the whole world is welcome to my home. Yes. Is the least of the A sigma witness to psi. Okay, and now we prove, and so now therefore, okay, so what do we have? So F is defined on almost mu, almost all sigma. So you know that F sigma mu from the other direction satisfies psi F mu, and then let me just put vector here. Okay. All right. So this is the main one of the main applications of normality, and it's important that it's defined this way, right? Because if you define the classic way, the ZFC way, then it's just then you cannot pick. Sigma is not well ordered. You cannot canonically pick a point. This A cannot be canonically picked if sigma is not well ordered. Okay, all right. So we don't have that's it. And so what am I gonna do next time? Next time, now we have the measure. We know it's unique. We know that Walsh's theorem is true in some cases. So next time we will prove two things. One is that I guess maybe one thing. So we will try to get an ultra filter in a generic extension, right, of a power set of reals. So basically, there are some classic theorems coming from the older times. When you add a real to L of R, for example, that generates an embedding from L of R into the L of R of the extension. So we're going to do things like that, but it will not be clear why the ultra power is well founded. So we will add. I guess we're not going to add. The forcing we do will generate an ultra filter over the reals. Right. Yeah. And we will see that. Oh, I see. Yeah. So as remember, NS is dense. Let me just backtrack why this is relevant. NS is, there is an omega-1 dense ideal on omega-1 if you have such a thing, then the generic embedding comes from collapsing omega-1 to omega, right? So we need to somehow take care of that extension. So that extension will add reals. And so what we do is we sort of mimic that construction in determinacy model. So we have this generic reals. Each generic real introduces an ultra filter over the reals. So we'll talk about this next time. And then we want to see that we have one Walsh's theorem for the ultra power, which will be a different proof than this one. And we also want to see that it's well founded. Okay, so Walsh's theorem will that's pure determinacy, has wage determinacy and things like that. But how are we going to argue that it's well founded? So this will be the key step, right? And to show that it's well founded, we have to show that its restriction, the ultra power embedding, right? So if you take the ultra power embedding and you restrict it to ordinals, you get the same embedding as by the super compactness measure that we defined by Soloway super compactness measure. So, but Soloway super compactness measure is countable, right? It's countably complete. So this ultra power is well founded. The ultra power by super compactness measure is well founded. Therefore, the generic one is also well founded because they agree on ordinals. Right, so that will be the key step, and then you'll see how all of these intricacies fit together. It's actually quite, I think it's really nice proof. So we'll do it next time. Probably it might be the case that we can finish next time. At least the main, sort of the main lemma, and then we'll see. Okay, guys.
I have something very short and pedantic to say. I think you want that S is closed under some pairing function. We need some pairing function S to this last part of the argument, because you reduced to things which are ordinally definable from a single thing in sigma, and not from finite sequences, right? So you somehow, because usually ordinally definable from elements of sigma, you can use finite sequences in sigma, right?
Mm-hmm.
And so you want some way of maybe the sigmas need to be even closed under some codalization or something. I don't know.
Right, maybe you need something.
Okay, sorry.
Yeah, no, it's a good point. I wanted to just give you the idea how these things are used, right?
Okay.
Yeah. Okay. All right. So let me stop this recording and all of pause recording.